Okay, so welcome to lecture number 10. I will take one more lecture number 11, which is next week, and after that, Ben is going to come back. Okay, so where do we stand? So we are dealing with operator learning. So here, we're dealing with operator learning. So this we already know. So idea is that if you have a PDE, which is given in this abstract form here, then the underlying solution operator is given by this object script G. And so this is a mapping from an input function. So function here to a function here. And we are going to learn this from data essentially, right? So from data, this is the other important term here, that everything has to depend on the data. So in particular, whatever operator learning framework or whatever learning framework that we're going to come up with, the key point is that the inputs and outputs have to be functions, but that's not enough, as we saw in a couple of lectures ago, that we need some notion of this equivalence between the continuous and the discrete, because without that, almost anything can be interpolated and we can get operator learning done. So now, inspired by traditional numerical methods, we came up with several ideas, to learn operators. And these ideas were spectral neural operators, TPO-nets, PCA-nets, and so on. This is where I essentially stopped in the last lecture. And the construction is exactly the same. So you have a mapping. The underlying operator is a mapping that goes between two Banach spaces. So here, and the idea is that since on a computer, we can only deal with discrete objects, finite representations. So what you do is first do a projection or an encoding, as it is called, to finite dimensions, then do all kinds of processing in finite dimensions. For instance, this is typically DNNs here, right? Deep neural networks, because these are function approximators, very powerful class of function approximators in finite dimensions. And then once you have a finite dimensional object, which is, let's say, a representation, some form of a representation of my input-output map, then I'm going to lift it up to infinite dimensions through this operator R. So this is the simplest way to do it, is to use a basis, and there are different constructions of basis here. So this led to the operator learning architectures that we have. We saw some numerical experiments. But of course, just by doing a few numerical experiments, you cannot conclude that something works and something doesn't. So in order to understand the nuance here, in order to understand what are the issues that come up, it's essential to do some theory. And I'm not going to do any detailed calculations, far from it, but just to make you understand what are the important issues, why this might work, might not work, we need to dive a little bit into the theory. Most of the theory that I'm going to present, actually most of the theory that exists, is based on this paper, Roberto, you can perhaps upload this paper up, right? So no one is asking you to read this paper. It's how many pages? 140 odd pages. So this is not the idea, but I'm going to just give you the key point. So remember, so now let's do a little bit of a recall. So remember that if you think of one way, there are many ways to think of it, but why did we think that, for instance, for pins, that if DNNs, actually shallow NNs is good enough, but certain neural networks, approximated functions, right? So this is what approximated functions to any desired accuracy. So this property of neural networks, deep neural networks, even shallow neural networks, was what was called as a universal approximation theorem. This was for functions. Functions are nothing but mappings between finite dimensional spaces and finite dimensional spaces. And underlying some of the success of deep learning is the fact that deep neural networks, they can approximate functions to desired accuracy. Very large class of functions, in fact, measurable functions. The right statement is that these are just measurable functions. So measurable functions include almost any functions that you know of, continuous functions, discontinuous functions like jumps, whatever you can think of. It's very difficult. I can, of course, construct non-measurable functions, but these one can accept are rather artificial. Anyway, so most functions can be approximated by deep neural networks. But now we are no longer dealing with functions, right? After all, our whole objective is that we are mappings between an infinite dimensional space and infinite dimensional space, Banach spaces or function spaces. So the question that one asks is, in the same way that deep neural networks approximated functions, can the objects that we constructed, things like DeepONet or SNO or PCONet, these kind of constructions, can they approximate operators? Okay, so the question that is, so here is a question. Is there a similar universal approximation result? And this is very important, because if there isn't, then there's probably, we are not going to approximate many operators for operators. For instance, with DeepONets, okay, let's just fix the architecture. The other architectures are very, very similar, and they are carried out in other papers. Okay, so is there such an answer? Is there such a construction? Is there such a universality? The answer, of course, is yes. That's good. So there is such a universality, and let me try to qualify what that is. So remember that, as I said, DNNs, they can approximate measurable functions. Measurable. And whenever measurable means that, essentially, roughly speaking, if you have a measure, the function should have some, you can write down an integral with respect to that measure for that function. And a similar result exists. So now remember that we had X. So this is my space. It's a very general space. L2 is a very, very large space, but you can do it over any Lebesgue space. You can take L1, for instance, integrable functions. There is no difference in that. And now you put a measure, a probability measure on that space, because in infinite dimensions, there is no Euclidean measure. You don't have the same measure in space. So you have to fix the measure, and then you take any measurable operator. So of course, I have to qualify, I have to take some operators between subspaces. So these are subspaces, but in particular, these can be L2 to L2. So you can think of the operator as a mapping between L2 to L2. This is also covered under the theorem. As long as it is measurable, there exists a DeepONet, in fact, even an operator network, which is going to approximate it to arbitrary precision. So E hat is the error. So E hat, here is the error between G, which is your underlying operator, and G star, I think I called it, no? How did I call it? No, I didn't, but we can call it as G star. So this is your DeepONet. Sorry, so this is the DeepONet. And as I said, the same results also hold for PCNet, SNO, and so on. So the error, now this is taken in terms of an operator norm, because these are operators, right? These are not functions anymore. But because these are operators, there's a very natural norm on them. I'm not going to tell you what that norm is, but there's a very natural norm. One can compute things based on that norm. And this is where the error is going to be small. So in other words, whatever you could prove for deep neural networks for functions, a similar result could be proved for operators with ONets, right? So this is a big result, because it tells us that a very large class of operators, in fact, any operator that you can think of, can be approximated by these objects. So it's a good, there's a solid theoretical foundation behind what we do, right? And this is important to know. If you don't have this result, then things could be dodgy. So that's the first conclusion. The second conclusion is, what are the caveats? Okay, this seems like a very nice result, but there are many caveats. In particular, we have, and we will see some caveats. This will force us to invent or discover or find new architectures. So in particular, the analysis is done in a way, because our operator at the end of the day, the G star, if you recall, is nothing but E composed with A composed with R. So there are these three pieces, right? The finite dimensional encoding here, the processing here, and the lifting here. So these are the three encodings. So each of these three errors contribute to the total error. So you have an upper bound, which is good, right? It's good to have upper bounds. So each of these pieces needs to be individually controlled, ideally, or at least as a sufficient condition, in order to bound this error here. But more importantly, and you'll see that this plays a big role, we also have what is called a lower bound. And the lower bound is enough with this lifting. Okay, this is based on some basis property, but it is based on this lifting. And this will come to its own. And both, and this is the point that I really want to emphasize, that let me use another color, perhaps red, because this is important. So both the bounds E are here and ER and E here. So the encoding bounds, encoding error and the reconstruction error, this depend on what is called the covariance operator. And if you remember, this is why I introduced PCNet, because this relied on the so-called covariance operator, right? So even though the DeepONet does not use a PCA construction, the theory behind it uses a PCA construction, and you need what is this covariance operator. Now, what is the covariance operator? Let me just recall it very quickly. So the covariance operator, so there are two objects which are involved here. So let's start with the encoding. Maybe encode, no. So for encoding, I used, so first, okay, let's rewind a little, revise a little. So what is, so given V belongs to X, so X is the space that you are dealing with, and mu is a probability measure on X. So the covariance operator, this is an operator now, right? So this itself is an operator, it's a map, it's C, it's an operator. It's roughly, it is exactly actually, it's just the expected value of V taking values in mu, or it's drawn from the distribution mu, V tensor with V. In other words, this is the integral over X of V tensor with V d mu of V. So you can identify, as I said, in the finite dimensional PCA, this was exactly my, if you do an empirical measure, so if you do Monte Carlo, this is 1 over M summation over K from 1 to M of Vk tensor with Vk. So this was the, and V is a sort of a, it's a vector, right? So the functions that we are dealing with is a vector. That's why we need this kind of a tensor product. And last time I defined what this tensor product was. So look back at your notes. So this is a function space version of this object here, because when you do a quadrature, you get this object. This object, in fact, can be worked with, one can work with it and so on. And what you look at is the eigen functions of this. This is, one can prove that it's a positive operator or a symmetric self-adjoint operator. So it has a spectrum, and let's say the eigenvalues of C are, let's say, lambda L, yeah, this is an operator now, so L equal to 1, 2, and so on, because it's a continuous object, and the eigenfunctions of C are psi L, for instance. So lambda and psi are the eigenpairs, and these are the objects that govern these errors that I just told you about. So as I said, for encoding, so now let me just change the color. So for encoding, you use mu, this is your underlying measure, and you look at the covariance operator C mu. So this is the object whose eigenvalues and eigenvectors, they determine the decay, or they determine the amount of error. Similarly, for the reconstruction, this is the same for what is called the push forward measure. So this is, so G is your underlying operator, right? So G is the operator, the ground truth. And what is this push forward measure? The way it is defined is the following. So this is a measure. So this is a probability measure on Y, because Y is the function space that we are dealing with. Our operator G is a mapping between X and Y. So what you do is that you integrate any function. So let's say f of W of Y, D of G mu of Y. This is the same as integral over X of f of G V D mu of V. So this is the definition, okay? This is just the definition of a change of variable, but it's a change of variable of a more complicated object. So in other words, in terms of intuition, so these are just some basic definitions. But in terms of intuition, what's going on is very simple, that so you have an underlying measure, you're drawing your data from this measure. I showed you some examples with Gaussian random field, but it could be something very, very different. It depends on what you're drawing from. So the encoding error, it has nothing to do with your operator. So this piece here has nothing to do with your operator. It just has to deal with your input functions, which is straightforward, right? So remember that you're drawing from functions. All your functions are very simple, so you could easily represent them in a few points, for instance. So this is easy to imagine. On the other hand, the other part, when you lift it up here, this depends on the push forward measure. So it not only depends on the input functions, but it also depends on the output functions. So this is roughly the intuition, and this makes this naturally plays a role. So it depends. Some operators are easier to approximate than some other operators. And in particular, if your input functions are drawn from a simple measure, like just imagine that all your input functions are going to be zero. There's nothing to be learned, right? So it's sort of intuitive that how you draw these functions also matters. So this is the first point that I wanted to emphasize, that it's not a free lunch. Even though there is universal approximation, it depends on very subtle things. It depends on certainly the input that you give in, more complicated inputs that you give. Maybe it's harder to approximate. It depends on the outputs that you get, because your operator takes some inputs and then it processes it and finds some outputs. You could have very complicated inputs, very easy outputs. That's all possible. Or you could have very simple inputs and very complicated outputs. That's also possible. So I'll give you an example. If you take the heat equation and you take very complicated functions as inputs, the outputs of the solution operator of the heat equation are very simple because it sort of smoothens things out. On the other hand, if you take the backward heat equation, it's the opposite, right? You start with very simple inputs. On Navier-Stokes, you start with very simple inputs. You potentially can get very complicated outputs. So this is just a sort of a precise way of quantifying these objects. So that's not enough, because the key, okay, this is important and it will play a role in 5 minutes. But more important than that is the fact, or an equally important fact, is what happens here. So this is what I described as the encoding error and the reconstruction error. What about the approximation error? This piece is also an important piece here. And in fact, by doing some analysis on this piece, one can show that the size of your neural network, the size of your depot net, so this is the depot net. I should have used different notations clearly because this is the same as G star. This one can show is the following. Okay, it depends on the following factors. It depends on this K. The K is a denominator. E is the error that you, okay, let me write it here perhaps, then it will be clear. Okay, one more page. It will be clear. So the idea here is that the size of your depot net, so let's write this because this is important. So operator that you want to approximate is given by G. The depot net that is doing the approximation is called G star. Okay. And then the size of G star, this is given by the size of the trunk net, the size of the branch net, and so on. This scales in the following manner for e to the power minus m of epsilon by k. Okay, and what are these factors? Epsilon is the error that you want. So for instance, if you want 1%, 2%, 5%, so this is the error magnitude or amplitude of the error. K is a measure of regularity. For our discussions, this could be, you could put K equal to 1. Okay, this is not important. This is not my point. But M epsilon, this is very important. And I think someone asked me a question about this last time, is essentially the number of sensor points. So remember that now we have to revisit what we did. So remember that for a depot net, for a PCA net, and so on. So this was for a depot net. M is the number of sensor points. So this is the projection that makes the finite dimensions, the number of points at which you measure the function, the number of Fourier modes that you're going to use, the number of PCA modes that you're going to use. So this is essentially the quantity that tells you how your infinite dimensional inputs are squeezed into finite dimensions. Okay, so this is a very important quantity, as you will see in a second. So this tells you, so this is the number of sensor points or Fourier modes, whatever you call it, or your SNO, PCA modes, and so on. So now what is happening? So remember that epsilon has to be close to 0. right? Let's say 0.01, but m, so to ensure that the encoding error, so this is the encoding error, if you remember. So encoding is this bit here, which tells you what is the error that you make when you take something infinite dimensional, input which is infinite dimensional, and squeeze it onto finite dimensions. So to ensure that this goes to 0, we have, this is obvious, that your m epsilon also goes to 0. This can go to 0 algebraically, this can go to 0 exponentially, whatever. It depends on the regularity of your measure, but this object has to go to 0. In other words, m of epsilon, go to infinity, what am I talking about? Sorry. Of course, this object has to go to infinity. We have to take more and more points, right? Otherwise, how else will so in other words, m over epsilon is going to be very, very large, right? So in order to make the error small, the number of points has to go to infinity. If not, you have a finite dimensional problem. If it stops somewhere, you have a finite dimensional problem. Because you have an infinite dimensional problem, your operators are infinite dimensional objects. What happens is that this quantity is going to grow. Sometimes it grows algebraically, sometimes it can grow exponentially, sometimes it can grow logarithmically, but grow it will. Otherwise, it won't be a infinite dimensional problem, it will be a finite dimensional problem. So this quantity is very, very large. So now look at what is happening here. So now this is something one. So essentially the size of G star, it grows like the order of 1 over epsilon, right? Epsilon to the power m epsilon. So 1 over epsilon goes to infinity, but so the quantity itself goes to infinity, but m epsilon also goes to infinity. So what is happening here? So you have two quantities, the base itself goes to infinity and the power goes to infinity. So in order to make small errors, you have to take infinitely large, doubly exponentially large size of your networks. Is this clear? So this is the consequence of the infinite dimensional nature of the problem. Because if it was finite dimensional, then this quantity will stop somewhere and you'll only have polynomial growth, which is the same as that of, you'll have some fixed growth, which is the same as that of deep neural networks. Because it's an infinite dimensional problem, you pay this price. And I think someone asked me in the last lecture about how you can just project onto finite dimensions. Well, you make an error while doing that, and the manifestation of this error is that you can have exponential increase in the size of your approximating objects in order to get small errors. So is this clear? So this is really an infinite dimensional problem. It's not a finite dimensional problem. Each time we're approximating it, we are making errors, and that consequence is seen somewhere. And this somewhere is here. So this is called a curse of dimension. This kind of a construction is called a curse of dimensionality, because the dimensionality is infinite. So it's not exponential, it's not a small, it's not 1 over epsilon to the power 100, because that would be finite, right? It's 1 over epsilon to the power essentially infinity. Okay, 1 over epsilon, for instance, to the power 1 over epsilon. So this is a very, very gigantic quantity. So what is the moral here? The moral is, even if there is universal approximation, there is a caveat here. So there is an issue. These sizes can be unrealistic because, okay, if, for instance, to get 1% error, I need to have something which is 10 to the power, 100 to the power 100. This is gigantic, right? So it's useless. So in a way, this analysis was very negative because it said, oh, come on. At the end of the day, you cannot cheat your way from infinite dimensions to finite dimensions. You have to pay a price. But there is good news. So let me just finish with that good news. But is this point clear? This is a very, very important point that I really want to emphasize. That you can't just approximate infinite dimensional objects for free. You pay a price in doing that. Either you approximate finite dimensional objects, that is okay, means this m is fixed, or things can grow arbitrarily large, exponentially large. Okay, but there is good news because this resolves. These were true for any operator. Remember, any measurable operator. This did not make any assumptions on the nature of the operator, apart from the fact that it was an operator and you could write it out. But now once you start, okay, by the way, is there any question? Did people understand what does it mean, exponential growth, double exponential growth rather? Questions? Everybody understood it? Okay, good. So then the point is, so there is a positive thing here. So the COD is curse of dimensionality. It's just shorthand because, so this is the curse of dimensionality. The point is, thankfully for us, one can always construct an example where this construction or the growth is actually exponential, and you cannot really, with a small size network or a reasonable size network, you cannot learn anything. However, there are some additional structure that one can leverage in order to sort of break this curse of dimensionality. DeepONet, but this is also true now for PCANet, SNO, all of these architectures, they SNO, all of them, they break the curse of dimensionality. Okay. And how do they do that? In what context do they break the curse of dimensionality? As long as your operator comes from PDEs. Well, it could also come from other places, but as long as it comes from PDEs, there is, or ODEs for that matter, there's a lot more structure to these operators than an arbitrary operator, because an arbitrary operator, I can take a random function and assign it to a random function. Take a random function, assign it to a random function. This is a very, very, let's say, chaotic object or a difficult object to handle. But the solutions of PDEs, as I said, if you have heat equation, for instance, you take very, very nasty inputs, but your output is going to be very, very nice, right? So you should be able to leverage that structure. And this is indeed done, but this, there is no universal result for PDEs. So this has to be done on a case-by-case basis. Many people did it, including me. And the idea is the following. So again, I'm not going into any details, but just to give you what's going on. So remember this example that I showed you last lecture with this forced pendulum. Okay, so this is an easy example of a nonlinear ODE. Similarly, you can take, this is your prototypical elliptic PDE. If you remember from the very first lectures, I have told you repeatedly that this is your elliptic PDE. And the operator that we take is the coefficient going into the solution itself. So this operator. And in both these cases, there is a lot more regularity than you expect. There's so much of regularity that not only can we can rigorously prove that the size of, this is the size of the, let's say the DeepONet, but it's the same result for the architectures. DeepONet, the size, it grows, but it grows only essentially logarithmically, the way I said it. So think of it as log 1 over epsilon. Okay, and log is a very, very slow growing function, so it's much slower than any power that you can think of. So there is more structure in them, and this structure is what is leveraged. So in other words, this sort of justifies the errors that you saw last time. If you remember DeepONet and so on, they were getting like 0.3% error. That's not surprising, because with very small size of networks, you can, in principle, approximate. In principle, it's important because there's also training, which is subtle. But in principle, you can approximate these objects. But you can go further. You can even take sort of nonlinear. This is Alan Kahn. This is a nonlinear parabolic PDE. You can prove similar results, but now it is not logarithmic. It's some algebra. I have no idea why this happens. Okay, so what happens here? So this is the D is your physical dimension. Physical dimension. What does that mean? This doesn't mean infinity. It's simply 1, 2, or 3. Navier-Stokes equations in 4 dimensions is useless, right? So you have this. These are small numbers. So this grows like 4th power. For instance, in 2D, it grows like how much? 6th, and so on. So this is a algebraic growth. Also algebraic growth for Navier-Stokes. So this is Navier-Stokes. Even for Navier-Stokes, which is a very complicated equation, the growth is only algebraic. Of course, it is worse than what it would be for an elliptic equation or what it would be for the ODE. So you cannot expect 0.3% errors for Navier-Stokes in general, because this already shows that. This would be logarithmically complex in error. This would be like, it scales like, for instance, in 2 dimensions, this scales like cubic. So much better than exponential, but cubic is cubic, right? In other words, to get 1% error, just let's do the math here. 1% error is 10 to the power 2, and this is, how much is it? 3. So 10 to the power 6, which means that your network will be roughly in the order of millions, right? And this is correct, right, Roberto? All our results are roughly in the order of millions. So it's not, the theory doesn't, it's not that off. You know, the ballpark, you can have a good idea how where it stands. You can also do hyperbolic PDEs. There are tons of different techniques that one uses. But as long as it comes from PDEs or ODEs, we sort of leverage their structure. These operators have more structure. And instead of having exponential growth, you have algebraic dependence. And algebraic with small numbers, right? So in all these cases, as I said, means this is 3 or 4. So in 3D, of course, this will imply that we need bigger networks, but that's not surprising, right? Because in 3D, we are heading more towards 100 million instead of around 10 million, let's say. But and anyway, this there are different techniques that are used, but the bottom line is still the same. That as long as the problem comes from PDEs, there is more structure. It's still not a joke, right? Because millions is not something small, or tens of millions is not something small. These are large numbers, but they are much better than if it would have been exponential. Because if it would have been exponential, this would be 100 to the power 100, right? So that would be the scaling at which you deal, and that's impossible to deal with. So this is the second important point. First important, or the 3 important points. The first was, of course, this covariance operator and the complexity of the task that you have. Second is the fact that you have the curse of dimensionality, because you really are dealing with an infinite dimensional problem, not a finite dimensional problem. But this can be alleviated, mitigated, whatever word you want to use, as long as your operator comes from PDEs. So these are important points, but this is not the end of the story. There's one more theoretical point I want to make. And this is here. So this is depot nets, but it's true for everything else, that SNO, PCNet. It's an important theoretical point. And this is to do with this covariance operator. As I told you, the performance of the network, or the performance of your operator network, depends on how fast or how slow the eigenvalues of this object decay. So this is, in fact, you can concretize it, because we have this following lower bound. Why is this? We have this lower bound, which is given here. So this is very important. Lower bounds are the best, because they tell you that whatever you do, that will be the error. It's because there's a lower bound on the error. So this is given in terms of the eigenvalues of the covariance operator, but of the push forward, okay, of the solution itself, rather than of the inputs. So it does not matter what inputs you give, as long as this is a complicated object. And how is complicated measured? It's measured in slow decay of its eigenvalues. Okay, if this is slow, for instance, if this decays only algebraically, then you can see that there is a square root here. So this will be so the error will be large unless until you consider a lot of modes, right? So this is roughly the idea. And it turns out that there are plenty of problems for which it is slow decay. So roughly speaking, the intuition is very simple. If you have a PDE whose solution operator takes very complicated things and squeezes them into something simple. Think of the heat equation. You take a lot of oscillations, lots of Fourier modes to begin with, and then you let it evolve through the heat equation. Because it's diffusion, all these modes get smoothened out, and you end up with something very simple, right? The high modes decay very, very quickly. So this kind of a problem, if you write down the covariance operator, it's not, it will take me half a lecture to do that, but it can be done. And then you'll see that this, because of this decay, all these modes, they will decay exponentially fast. So there will be an exponential decay, which means that with a few modes, you can capture the entire situation. So this is what happens for heat equation, for instance. However, there are other kinds of problems, typically transport-dominated problems. For instance, I'll give you an example. So if you take, for instance, this is your initial data, and you're transporting it. So the initial data is just being moved like this. It's just being moved in the domain, right? So this is how the solution looks like. So in this case, the matrix, if you think of this covariance operator as a matrix, which you can do if you have finitely many points, or you discretize it, then the matrix would have the following structure. It would have 1, 0, 0, 0, 0, 1, 0, or 1, 1 rather. Sorry. Roughly speaking, it will have a structure which looks like this. 1, 1, 1, 0, 0, 0, and so on. So you see, so it has this cascading effect of lots of ones and zeros, but the one is only being shifted to one place. And then it's very simple. You can either code it up very quickly, or you can try to prove it by yourself, check it out yourself, that then the eigenvalues are going to decay very, very slowly. Okay, so transport this kind of step functions, for instance, they make the eigenvalues decay very slowly. Because of that, you need lots and lots of modes. So for a small size network, you would expect that the errors will be large. So this is the intuition, this is what the theory tells us, and indeed, this is what happens. So if you take an equation, you can do it with the transport equation, we'll see that in a bit. But let's take a slightly more complicated equation, the transport equation, which is the Burgers equation. Inviscid Burgers equation, not the viscous. Nothing annoys me more. Three things which annoy me in this context. One, the room that we are sitting in, because it is always bad air. Second, the time that we do it, because I don't get to eat, and I don't know how you guys manage, but I do very poorly. And the third thing is the problems with Zoom. They really annoy me. You know, but the point is I can't take it out on you guys because there are no exams, so there are only projects. Otherwise, I could have. I'm kidding. I don't know that. Okay, so take the Burgers equation. I write it in the form that I write. Okay, so this is the Burgers equation. And then essentially what happens is that if you take initial data, so if you take initial data like this, after some time, you have the formation what are called shock waves. So you have solutions which look like this. Okay, and here we did the same, just like we did last time. We took Gaussian random fields. Remember this? We looked at them in the last lecture. We took Gaussian random fields as initial data, and then we just computed it, trained a depot net. In this particular case, this is a depot net. And remember, the depot net suffers from this problem. Here, the eigenvalues, they decay even more slowly. You can show that the decay is worse than linear, at least it's linear. So this will be a very slow decay, it's not exponential decay. You need lots and lots of modes in order to get the right kind of error. And you see that in practice also. So for instance, the ground truth here is in orange, and the prediction, well, it does predict that there are shock waves. So these are typically shock waves. It does predict that, but they are completely off in the location, in their amplitude, and so on. So actually, the error is at least 30%. It's more, but let's say a conservative one is 30%. And so this is how much more than what we saw for the pendulum, 2 orders of magnitude, right? 0.3%, I can always live with 0.3% error. 30% is useless. You can't build a bridge or a rocket or an aircraft with 30% error in anything, right? This will blow up in no time. So these are the issues, okay? So in addition, even if you have good complexity bounds, and saying that the network is going to grow exponentially, but the number of modes, the size is also dependent on the number of modes. This depends on the slow decay of the eigenvalues. For instance, in particular for transport-dominated phenomena, but there are also other problems. Each time this number is the decay is going to be slow, it simply means that the solution that you're dealing with is very complicated. It's a proxy for that. It's a quantitative measure of that. And then these kind of methods, they might fail, and they do. Okay, so this is, so whenever you have been given a situation, of course, in many cases, you have everything is smooth, like you have the solution of the heat equation. This will work, or the pendulum, this will work like a charm. When you step out and you have more complicated problems, then there's going to be an issue. So now in the next 1.5 lectures, so the half lecture today and the lecture tomorrow, and not tomorrow, next week, I'm going to explain, are there some ways in which this can be remedied or rectified? Okay, so let's take a break because okay, let's meet at 1:15. I was thinking of giving a shorter break, but we also need to breathe. Okay. You will, I need to pause the recording. So now let's try to find if there are alternatives, right? So this was where we stopped. And there are alternatives, and as I said, we will explain that in today as well as in the next lecture. And one basis of alternatives is what are called as neural operators. And this is what I'm going to explain now. I could have started with this, right? Because it's a very natural construction in some sense. So neural operators. Yeah, so this is the alternative. So, okay, so what is the idea? So the idea is, if you remember, what are deep neural networks, DNNs? So you have a mapping. So you have your, let's say, your ground truth function. Now I'm searching for notation a bit. Let's say that your ground truth here is a mapping between some input space to some output space, right? D out. So this is the underlying function that you want to approximate. Now, the way we do it with the DNNs is through this compositional construction, right? So we have all these layers, and we push the input, the vector, because now it's a vector. It takes values in RDN. We push it through different layers. Now, each single layer, of course, has this construction here. So this is your weight matrix. Perhaps maybe I explained it a little. So each layer. So now for a DNN, so what we do? So the input, let me call it as a vector. Did I call it as? Okay, I didn't say anything. So I could, for instance, the vector is YL. So this is the input, and the output is another vector. YL plus 1. So this is at the LF layer. And the way it functions is the following, that YL plus 1 equals to sigma. So this is your activation function, AL of YL plus BL. So this is a, and let's say that YL belongs to RDL, and YL plus 1 is a LD plus 1, DL plus 1 vector, right? So AL is a matrix. So this is DL plus 1 times DL, and BL is another vector, DL plus 1. And this guy is applied pointwise. In other words, sigma of U is, or sigma of U1 up to UN is equal to sigma U1, sigma U. So this is sort of the pointwise application of the nonlinearity. So this is how deep neural networks operate, right? So neural operators, what they do is, and then there is a composition. So these layers are being composed with each other. So the idea behind it is, in a way, fairly simple. So instead of going through what we did with finite difference methods, or traditional numerical methods like finite difference, finite element, where we had this sort of very elaborate construction, if you remember, we can just, so this was a construction that we have, by the way, everything is somehow equivalent. But so the idea here is that is, at least pedagogically, instead of, we still have a composition. So remember that this has to be an operator, neural operator, NO, not no, but NO. And this is the sort of construction that is there, where we are going to generalize this compositional construction to infinite dimensions. And so, in other words, so we know what a DNN is. So it's this layer-wise composition. And now we similarly have the following composition. So we will have N is equal to N1 composed with N2 composed with N capital L. And each of these NL is an operator. So earlier, each layer was a function. So this was the function. But now we want this to be an operator, which means that what is an operator? It takes as its input something which is finite dimension, which is a function, and returns also a function. In other words, NL is going to take a function, let me call it as VL, and map it onto another function, which is VL plus 1. So VL and VL plus 1 are some functions. We need some assumptions on them. So for instance, we could say that VL plus 1, these are continuous functions. Okay. It could be also regular function or integrable functions, but let's say that these are continuous functions which belongs to RDL or RDL plus 1. Because of course there is bound to be a difference between them. So we could do that, but these have to be functions now. So this implies continuous functions. So the inputs and outputs to each of these layers is going to be functions. Okay, sounds good, but how do we do it in practice? This is an attempt, but so more things are broken than just the table. Huh? I don't want to follow. My back can be further ruined. But okay, so now you have this, but the way it is done is exactly by generalizing this construction. So if you look at this construction here and you take it, abstract it out, there are three elements. First, there's a bias vector, right? So you have a bias vector, which is BL. And now bias vector, so the input was a vector, the output was a vector. So it is very natural. You replace with a bias function. In principle, in practice, of course, we can't store functions on computers. We have to work with something which is discrete, but let's wait for a minute. So now we can replace it into a bias function. So BL becomes a function. Earlier it was a vector. Now the key term is this AL. So ALYL. So this is a matrix vector multiply, right? For infinite dimensions multiply. In other words, this is a matrix is the most general form or a general form of a linear function. Actually, the whole thing is a general form of an affine function, but a matrix, so matrix vector multiply is the most general way in which you can transform a vector linearly into another vector, right? So this is the basic idea. So now we have to find an infinite dimensional analog of this construction, right? So we need an infinite dimensional analog. So infinite dimensional form of matrix vector multiply. And mathematics in the form of functional analysis suggests several different ways, but you'll see that there is one particular intuitive way. And this intuitive way, let me call it as L. So instead of a matrix vector multiply, L is a mapping which takes V, and which is a function, and puts out L is a mapping which takes V and puts out LV. So L is a linear operator. But now instead of linear operators are very general. Okay, one possible characterization of them is in the following manner. LV, which is now a function, evaluated at a point X, is given by the domain. So we are using the same domain. You can also transform that. K of xy of v of y dy. Okay, so a matrix vector multiply is now replaced by what is called as a kernel integral. And why is this a generalization of a matrix vector multiply? So it's very simple, means x and y. So now the integration is with respect to the domain D, right? So now use, let's say that we use Monte Carlo to do a quadrature, or let's write it poorly. Use Monte Carlo quadrature. So this guy here can be approximated by, let's say 1 over m, then summation of whatever, give it j, for instance, 1 to m clearly. So k of xi yj of v of yj, and this is going to be lv at xi. So instead of having a domain D, now I break it into little points. Quadrature points, these are random points, but you could also do more structured quadrature points. And this, if I use a matrix, so let K, capital K, for instance, Aij is little k of xi yj, then LV I, the ith value, is given simply by 1 over m, for instance, is given simply by kv I, right? So so this guy becomes a matrix. It is multiplied with a vector, and you take the ith row. So now you can see that instead of having matrix vector multiplies, so this is what we were aiming at, a sort of a function version of it. is given in terms of this kernel integral operator. Any questions about that? This is a very important point. So a natural way to generalize matrix vector multipliers is to use this kind of kernel integral operators, always integrate against the kernel. I'm sure you have seen this construction somewhere in functional analysis or electrical engineering. This is a very common way to proceed. Are there any questions about that? So this is very important point, right? So how do I generalize a matrix vector multiply? I have to use a kernel integral operator. Okay, and this is precisely what is for the time being. This term is also important, but perhaps I can set it to 0 for the time being. It's important. It will come in a bit. So all that I do, that instead of having a bias vector, I replace it into a bias function, and instead of having a matrix vector multiply, I replace it by what is called a kernel integral operator. So this is it's still not finished. So this just replaces the affine part here, right? The linear and the constant is replaced by a constant, not a constant, but a function, and by a kernel integral operator. But I also have nonlinearity, right? So the nonlinearity, how do I do that? I do it pointwise. What is the meaning of this? So this symbol here means sigma f is a function, and because it's a function, I have to evaluate it at a point. Sigma f of x is nothing but sigma applied on f of x. Okay, so this is just like we did it with I think I wrote it down somewhere. No? Here, for instance, just like I wrote it down, that each thing is evaluated at every element of a vector. So pointwise, you evaluate it at every point in the domain with respect to the function. Okay, so this is a pointwise application of a nonlinearity. And Viola, we have a neural operator, right? At least an operator, because all that it does is that the input is a function v, right? So the output NL of v, which is the output of the nth layer, can be evaluated at any point x in principle. And the way it is done is that we have a bias function, which of course has to be parameterized in some manner. This, for instance, can be a deep neural network or some other construction, a parameterized function. And then we have a kernel. This is also parameterized. And how it is parameterized matters a lot. And then we will compute this kernel integral. So if we knew how to compute functions to functions, this is the way to do it. And it is a direct generalization of neural networks to operators. Hence, they call it as neural operators. So this is the sort of justification of the name. Okay. And of course, as I said, at the moment we set this to 0. This does play a role, but these are all parameterized. And these are parameterized, for instance, by neural networks or other parametric functions. So during training, you have to learn these, right? So is this construction clear? How this is done? It's a sort of a verbatim translation of something that we do in finite dimensions to something that we do in infinite dimensions. Okay. Any questions on this? Also, no one on Zoom ever asks questions. So okay. So yeah, that's a very good question. But now we will come to that. This is sort of does the emperor have any clothes, right? I mean, this is a question of that type. It's a very important question. How exactly are we going to do integration? Because we don't know how to compute integration by hand. If we did, that would be great, right? But we have to make some approximations. I'll do that in a bit. But because of different names of kernels, you have different types of operators, and I will teach one with some, and also in the tutorials we'll cover one of them in some detail. But now to the question that you asked, how are you going to do this integration? I need to provide a little bit of context. So now, so this is the key point here, right? So let's do a little bit of a recall. So my neural operator, this is the neural operator. By the way, when I'm writing and with this thin font, I don't see anything, but do you guys see it well? Yeah, okay, because with my eyes, I certainly are not able to see what of course I can see it here, and I can't turn back all the time, but so you have to tell me, because to me it looks very, very thin, almost nothing. But okay, so neural operator, if you recall, is This is a little bit more general than this, but let me write it in this way. N1, so composed with N2, composed with NL, right? And the nth layer, NL, applied on any function V, so its input can be any function V, is now given by sigma of the kernel integral, KL, of course, now there has to be a L, KL of xy, V of y, dy, plus BL of x. BL is a function, so there's no ambiguity here. Okay, so this is the object that I have to evaluate. But of course, at some point I have to do integrations and nothing. This seems like a very sort of nice, tight construction. The answer is no, right? Because at the end of the day, I cannot work with functions. I have to work with some discrete representations of the functions, point values, basis coefficients, whatever. Means I have to work with some discrete versions of the functions. Let us say that we are so we evaluate functions, or we replace a function, or discretize, maybe is the right word, because this plays a role. Discretize V, the input, by V of x I from 1 to capital N, for instance. I'm just taking a number here, 1 from capital N. So these are point values. And this is what is available to me. So I don't have the function, I just have its point values, which I store as a vector or array or tensor, whatever data structure you like. There's no preference. Then I have to similarly, so I can only do the following. NL of V evaluated at the point xi. That's what I can do. I can evaluate at those points is equal to sigma. And then this term is very easy. This is BL of xi. As long as I have parameterized the function, I can evaluate it. But now I just have the integral over d of KL of xi y, v of y, dy. But I don't know how to integrate by hand. Only very simple functions. We can only integrate very simple functions by hand. How do we integrate this function? So when we can't do an exact integration, what do? We do a quadrature, right? So this is the only way to do it. So we use a quadrature. And it does not matter to me what quadrature rule that we're using, but we could, for instance, approximate this construction by the following. So no, not integral, it will be replaced by sum. So what is the sum? So it is summation over j from 1 to, let's say, n. So we have n points. The same points where we're evaluating the functions are the quadrature points. For simplicity, these can be different. But and then it is KL of xi yj. So essentially, I've stored it as a n times n matrix. And then this is so v of yj. And some weight, right, omega j plus BL of x. So this is how you evaluate it in practice. So you have to do a quadrature. Now everything is computationally possible, right? Because I know what these numbers are. I know what these numbers are. This is the input function that I'm sampling at these points. I can evaluate these quantities at each point. And I can also evaluate the kernel, but I have to evaluate the kernel on this tensor product grid essentially, right? And then I just write it down. So now you can see, so it's a very simple construction. However, there is a caveat. And so what is the computational complexity of this entire thing? Computational complexity is that for each point xi, okay, this is at least of the order of n, because I have to evaluate these points at n different points, n different yj's, and then I have n i's, right? So 1 is less than I, j is less than n. So these are matrix vector multiplies, but the complexity here is of the order of n squared. So it is quadratic in the number of quadrature points, okay? And quadratic in the number. Now imagine that you're in 2D, okay? And now you're on a 100 by 100 grid. 100 by 100 is nothing, it's a small enough grid. So you have 10,000 quadrature points, 10 to the power 4. But your computational complexity is not 10 to the power 4, it is 10 to the power 8, right? Because you have, so 10 to the power 8 is 100 million. Is that correct? Yeah. Yeah, always I make these mistakes, but it's 100. is 100 million, and that's the computational complexity is very, very big now, right? And just imagine this is per layer. So now you have many layers. Let's say you have 10 layers. So that's a billion parameters. That's a billion minimum, a billion number of operations, which is a lot. Now just imagine trying to do that in 3D. You're out of memory. You're out of everything. Compute very, very quickly. So you see, so it's not a free thing to do a matrix vector multiply. We already know that if the matrices are very big, then the matrix vector multiply is large. But here, we're not doing a matrix vector multiply. We're doing an integration with respect to a kernel. So this is going to be a very, very large number. It's not a finite dimensional value. It grows, and it grows in this following order. So it's quadratic with respect to the number of quadrature points. And we don't like that, because that's too big, right? So we have to somehow thin it down. We have to make it sparser. Just like in matrix vector multiply, we put more structure on our matrices in order to have it not explode quadratically, but by something else. So one has to use some ingenuity, because doing a kernel integration like this is not going to work. So in fact, we will do two tricks in order to simplify this, or in order to make it the complexity to be manageable. So so there are, as I said, there are these different people use low ranks, for instance, or multiple expansions. But the one that I want to introduce, and the one which is often used in practice, so is this point very clear that there is a complexity issue? Just to do computations with these objects is going to be very, very expensive. So the solution, one solution, is to use what are called Fourier neural operators, and this is. And we have this as we had it as one of the project tasks, right? Yes. Okay. In particular, one can use Fourier neural operators for that. So these can be very useful in some contexts, as we'll see. So FNO, this is what they are called. Now, how does Fourier neural operators work? And this, let me explain to you with some little bit of detail, so that you understand what's going on. I will, of course, summarize the contents of this slide, but let me explain a little. So the challenge is, how do we reduce this quadratic computational complexity? Because it's a very high number. So what can we do? Why am I not seeing the page? Oh, here. Okay, so what is the principle behind FNO? And then in the next tutorial, they are going to explain this to you at a code level. I explain the concepts, and the practical realization these guys are going to explain. So FNO. What is the basis of FNO? So recall that we have NL. This is the... Okay, so perhaps let me explain the kernel. This is the most important bit anyway. So this is, as I said, V of X is given by this sigma of BL by S plus the kernel integral, right? So KL XY F of Y dy. So now first, remember that this kernel is something that we have to learn. No one gives us the kernel, right? It's something that we have to learn. But instead of having an unstructured, very general kernel like this, the first point is, it's not an assumption, but first trick maybe. Trick, and what is the first trick? Is that instead of having general kernels, so this is replaced by, and this is a very obvious trick, by something which is translation invariant. Okay, so instead of depending on essentially the tensor product, you are only taking things along the diagonal, and that's going to be a very, very big thing. So in other words, this operation here, what is this operation now? So this is KL. So this integral here, KL of X minus Y. Why did I write F when I only have V's? Good question. The answer is obvious, right? Function, the first thing that comes to your head is F, not V. But okay, this is nothing but a convolution between KL and V. So this is a convolution, a continuous convolution. In fact, in the next lecture, we are going to directly work with a convolution in physical space, so leading to convolutional neural operators. But today, we are going to do this in Fourier space. So the main idea, so this requires red. So main idea behind FNO is perform convolution in Fourier space. So first, let me explain what Fourier space is. Then I'll ask you guys, why is this a good idea? Okay, why should we do things in Fourier space? So let's introduce. All of you should know this. This is very basic signal processing analysis, depending on whatever background that you are from, right? So now let me fix some notation. Let us have a function. So first, there is a Fourier transform. So this is a mapping F. So it's an operator. It's a mapping which takes functions which are square integrable, because without that you can't take the Fourier. Well, you can take Fourier transform for very, very general functions, even distributions, tempered distributions. But let's take square integrable functions, and these are functions which live on some domain D, and whose values are, they can be complex valued, because anyway they can also be real valued, but we can just work with complex values, because anyway the Fourier transform itself is going to do it complex value, right? And this goes to little L2, the sequence spaces on the lattice ZD, and this takes values again in complex value. You can't avoid being in complex value. This you can avoid being in complex value by taking it real value. But let's keep it complex. D is in RP. Okay, so what does a Fourier transform do? So fix. So this remember that the functions are going to be vectorial functions. This is important. Of course, you can do it with scalars. Fix J between 1 and I think I called it as N, right? The target, the vector space, the target vector space is N. So fix this. Then the Fourier transform of Vj, I take the jth component of the function. So V is the function. So I'm going to evaluate the Fourier transform of V. So I take Vj. And remember that this now has to live in the lattices. So I have to take K. So K is along a grid or along a lattice. I take any K, which is often called the mode, the Fourier mode of the function. So this is equal to the integral over D of V of x, psi K of x dx. And what is psi K? Psi K of x is given by e to the power. It depends on how you normalize, but I generally normalize it like this. K in a product with x, right? So this is just a Fourier transform, nothing special. I just don't want to write the exponentials, the complex exponentials all the time. So I write them as in terms of this. Okay, I always write them in terms of this psi k functions. So these are the trigonometric or complex exponentials, trigonometric polynomials, whatever you want. So Fourier transform is take a function, integrate against the complex exponential j, of course. Otherwise, it's a vector, right? So this is the Fourier transform, and then the range itself, the target, it takes values on the lattice, right? So at each point on the lattice, you have this. Now the inverse Fourier transform, that's also a very important object. So in other words, given a function, you break it down into its harmonics. That's the Fourier transform. Inverse Fourier transform is recollected from the harmonics, right? Inverse Fourier transform, I will call it as F inverse. Now this is a mapping from the lattice and complex dimension here, Cn to L2 of dCn. And it's just the other way around essentially, right? So I need a page. Why am I using the Fourier transform? We'll see in a second. Okay, so the inverse Fourier transform of a function W now, or did I call it as W, the coefficients? Yeah, the jth coefficient at the point x is nothing but the summation over j belonging to the lattice of Wj psi j of x. I think I might have missed some normalizations, but that's not the point. So in other words, this extracts the coefficients. Fourier transform extracts the coefficients with respect to the trigonometric basis. Inverse Fourier transform builds the function from its coefficients. Okay, so this is the relationship between them. And the good thing about the Fourier transform is the following. So if you take the Fourier transform of the convolution of any kernel or any function, so what happens to the Fourier transform? So I take two functions, I convolve them, and I take the Fourier transform. Then what happens?
It's a multiplication.
It's a multiplication. That's very good. So in Fourier space, this operation is going to be a multiplication. Okay, so why do I care? In other words, since this is the case, if I take the inversion, I can always take the inverse Fourier transform. Then what happens? This is F inverse of f of k, f of v. Okay, in other words, so this is F inverse f. So this implies that k convolved with v, convolution can be rewritten in Fourier space or through Fourier space in the following way. So I take a function, take its Fourier transform, take the kernel, take its Fourier transform, multiply them, take the inverse Fourier transform. It is the same as doing convolution. Okay, so that is the basic idea. But why do I care? Why should I take the Fourier transform? What do I gain? Remember that we had this issue with computational complexity. Now the hint is, suppose I am on a uniform grid, means of course this has to be done discretely. Suppose I am on a uniform grid, some equispace as it is called, something like this. Then what is the property of the Fourier transform that will help me in dealing with the complexity? Or how can I efficiently compute the Fourier transform and the inverse Fourier transform on a grid? Yeah, who is going to say this? She's saying, you want to say it? FFT. Okay, so this is FFT. And this is the whole point of this construction in some sense, because at least if you're on a uniform grid, because at the end we have to deal with, so it's the Fourier transform, you have the discrete Fourier transform, and this can be done very efficiently by using the FFT algorithm. And FFT is probably the most important algorithm from the last century, right? It was probably, who knows what is the most important, but it's one of the most important algorithms. And the advantage of FFT is that instead of order of n squared, FFT, what's the computational complexity of that? Who knows that? Yes, please. N log n, very good. So that's a huge saving, right? So instead of having, now imagine that we had n squared was, n was 100 times 100. So this would be 10 to the power 8. Instead of that, so it's 10 to the power 4 log 10 to the power 4, which is nothing, 4, right? So this is a huge saving. And in practice, this is a huge saving. So this is sort of one of the reasons, one of the logic, or the logic somehow, behind the construction that I showed you, that you can do things efficiently in Fourier space, provided that you have a uniform grid. So either in many applications you have a uniform grid, or you can convert your problem to one on uniform grid, then use FFT, so that this curse that we had of the kernel, order of n squared, this is removed, and instead you have order of n log n, right? So this is the key. But there are some, so this is the main idea. So the main idea is that you have a convolution in Fourier space. But there are some more tricks that are necessary in this construction, which I'm going to sum. This also has to be done in a reasonable manner, and this is what Roberto, you guys will do it in the next lecture, right? In the next tutorial, they will show you in practice how this is going to be done. I'll just finish by pointing out two additional, or not two, but yeah, two additional things that one has to keep in mind. The first is that, so this is the construction. So remember that these are the Fourier layers. These are the layers that we have just shown you. And actually, I just said that this is where you use the FFT. And by using the FFT, you can do this operation fast. But there are two additional tricks. The first additional trick is that you have what is called a lifting and what is called a projection. So lifting and projection, these are linear layers. Sometimes people can also use nonlinear layers. And the idea is that the whole point of machine learning is representation learning, that you transform your variables into some latent space where there is some better understanding, or there is better feature extraction and so on. So how does this work? So you have a function. So A is your input function. And this is typically a function, let's say in L2 of D, R D0, for instance, because it's the zeroth layer. And then what you're going to do is that you're going to transform it by P. So this is this P here. You're going to transform it to a function which is sitting in the same domain, but now it's in a very different, let's say, a latent space. So this is a latent space lifting to a latent space. And the latent space is going to, it's similar to what we do in convolutions, for instance, where we, convolutional neural networks, where we mix channels or increase the number of channels and so on. So in other words, all that I have to do is that your P now is just a R D1 cross D0 matrix. Easy to learn, right? It's just a matrix. And nothing is more annoying. So it's a D1 cross D0 matrix, very easy to carry. And this is the same matrix at each point. So this is important, right? So PA of, then you act as PA of X. I'm very sorry about this. I don't know what's happening to my arms. Okay, so this is what is called a lifting to latent space. First you lift, but it's the same lifting for every point. Okay, it's just change in feature space. And projection is projection from latent space. So it's the same operation. So let's say that you do this layers. I don't know why there's a T here. Let's say that there are L layers. So now the output of this, now let me write it here. So projection. So P, Q, my apologies. So Q is a mapping which takes, let's say L2, it's better than L2, but D, R, D, L, back to R, D out, back to R, D out, same kind of thing. But the difference is now D1, I don't understand this. So D1 was much bigger than D0, and DL is typically much bigger than D out. May not be much bigger. So you take a function which has only 3 components, let's say solution of Navier-Stokes in 3D, but you lift them into, I don't know, 20 components. You do your processing from 20 to 30, 30 to 50, 50 to 60. And then from 60, you have to come back to 3 components again, because at the end of the day, you have the solution of the Navier-Stokes. So the vector has 3 components in the velocity. So you have to project it down. So you go to a high dimensional latent space, do your operations there, and you come back to a high dimensional, but not that you don't change the domain. The domain is still the same. It's only the target, the phase space, that is going to change. So this is one trick, and this plays a very, very important role, this lifting and projection, because as I said, the key is to learn features, and these can be best learned in latent spaces, which are learned on the way, right? Because we sort of find that. The second point, which is often ignored, and which I ignored before, is to have this kind of what is called a residual connection. And this plays an important role. Perhaps I'll highlight it in the next lecture a bit more. But the idea is that already in the neural operator, I had just thrown out the entire, so I had just processed it out. But you know that I think Ben also showed you ResNets. Is it possible to show them in the tutorial to take out some of these things and then see what happens? Or right, that would be a possible idea, just to take out. For instance, we know that if you take out the residual connection, you will do worse, right? So this is just a way to retain some part of your signal. So you start with the signal, you retain a part of it. How much you learn through this weight matrix? Again, it's a pointwise matrix, so it's acting on the same, just like the projection and the lifting operators. And then some of it is passed on. And the rest you do, you take a Fourier transform. So your function, you convert it into the harmonics. You do the parameterization. Your kernel was in Fourier space. So this was, I forgot to say that. So this here, Fk, I just write it as R. And this is theta, because we don't do anything in physical space in terms of the parameterization here. It's in Fourier space. So you do a multiplication in Fourier space, take a Fourier inversion, and pass that signal, and keep on doing it. So this is sort of the construction, and this is what is FNO. The practical details of how this is done in practice, the guys here will explain you in the tutorial on Tuesday. But in the next lecture, we will see whether this architecture helps us overcome. First of all, computationally, it's okay, right? Because of the FFT, we know that this is tractable, this is n log n, this is not order of n squared. But does it work in practice, right? Does it remove some of the problems that we were dealing with? So this is going to be where I stop. Okay, and we meet next lecture. I'm going much slower than I expected, so I have to hurry up in the next lecture. So less writing and more just showing slides. Okay, meet you on next Friday. No.